Okay, I hope everyone can see my screen. Yeah, the second half, we're gonna begin with an example. So in this example, we have a mass, spring, and damper. Maybe let's assume the value of the component. Maybe we have, sorry. Okay, we may given a mass is equal to 100 kilogram, and maybe the spring constant is equal to maybe 400 Newton per meter, and maybe the damping coefficient C is equal to 200 kilogram per second. So I want you to check why the unit of the damping coefficient is equal to kilogram per sec. We may begin with, we know that the unit of the force is equal to the unit of the damping coefficient multiplied by the unit of the velocity. So the force is the Newton or kilogram mass per sec square is the unit of force. MA, kilogram mass per sec square. And the unit of the C multiplied by the unit of the velocity or meter per sec. So yeah, from here we can see that the unit of the damping coefficient should be kilogram per sec. Yeah, if the problem gives the value of MCK, the mass, the spring coefficient, and the damping coefficient, and how can we find the natural frequency, the undamped natural frequency? How can we find the damping ratio? And how can we find the damped natural frequency? And do you think the system, does the system oscillate? Does the system oscillate? Yeah, do you have any idea on this? How can we obtain the natural frequency? Yeah, the natural frequency is equal to square root K divided by M. So you can compute the natural frequency. How about the damping ratio? Damping ratio is C divided by 2 square root Km. So you also can obtain the damping ratio. The damped natural frequency, you also can obtain it. Omega D equal to the natural frequency multiplied by square root of 1 subtract by the phase square. So how about this question? Does the system oscillate? The system will oscillate only when the damping ratio is between 0 and 1. If the damping ratio is more than 1, the system does not oscillate. And the next thing to the problem like this is the initial condition problem. What if we give x0 maybe equal to 0.1 meter and v0 is equal to 0 meter per second? How can we find the response and plot it? So yeah, in this case, if we find the omega n, the square root k divided by m is square root k divided by m is equal to 2 radian per second. How about the damping ratio? It's a kind of like, yes, C is 200 divided by 2 square root of 400 multiplied by 100. So what we get 100, and here will be 100 divided by 2 of 100. Yeah, in this case, the damping ratio is equal to 0.5. So in this problem, the system oscillates because the damping ratio is between 0 and 1. And the vibration will be underdamped, free vibration, underdamped vibration. Oh, wait. Yeah, it's underdamped vibration. So if we want to find the response, we need to go back to the form of the solution xt. Yeah, thank you. Okay, can you still see the black box, or it disappear? Yeah, I hope it disappear. Okay, if you still see the black box, just text me again. If not, I will assume that it's already disappeared. And okay, if we back to the case of the underdamped vibration, yeah, here the form of the response is written in the form of the magnitude of the exponential decay multiplied by the psi function of omega dt plus the phase angle. So the response will be the response will be A multiplied by the exponential decay and psi omega dt plus B. And we know the x0 and v0 and yeah, by the initial condition problem, we already derived that the cosine of the phi angle is equal to v0 plus psi omega n x0 divided by a omega d. And we also know that the cosine, no, the sine of the phi angle is equal to x0 divided by a. And we can solve for a and phi by the phi equal to the arctan of the psi phi divided by cosine phi, and we can obtain A by this relationship, and we can plot this response. So how can we plot this response? So in the next slide, I will show some code in MATLAB. I'm not sure all of you have experience using the MATLAB program or not. But let's see the things here first before I try to copy the code and run the program to see how it plots the result. We're gonna see line by line of the code. What is the meaning of the code in the MATLAB program? In the MATLAB program, I put the variable that contain the value of the mass in the unit of kilogram, 100 kilogram, and the stiffness and the damping coefficient. This is the value of the parameter of the system. In MATLAB, we don't need to define the type of variable. So it's simple for you, easier as compared to Java or like C language. Yeah. And here, the green one is the comment. After the percent symbol, it will be the comment. So the code won't compile this thing. I just put the comment so that you can understand the program. And yeah, for the natural frequency, we compute the natural frequency by the square root k divided by m. If you don't put the semicolon at the end of the line, the program will show the result of the computation. But if you put the semicolon, the program will store the data, and you can click into the variable to see the value of the variable, but it just not disappear automatically on the screen, but you can click to see it. The damping ratio, okay, the natural frequency square root k divided by m. the damping ratio is equal to damping coefficient divided by 2 square root km. So C divided by 2 square root km is the damping ratio. And the natural frequency, omega d, is equal to omega n square root 1 subtract by theta square. And the initial condition, we have the position, initial position, and initial velocity. And if you remember here, this one and this one, I write the program to compute A psi phi. A psi phi is equal to x0. Is what we have here. A psi phi is equal to x0. If you want, I'm not sure you can catch up, but if you go back into here, it comes from here. You have x equal to this, and you find the time derivative of this. You get this, and x0 is mean x when t equal to 0. When t equal to 0, the exponential decay terms equal to 1 and t0. So sine omega dt is 0, has only the phi angle. So it comes from here. So V0 comes from this line, the equation 2. So yeah, here, A psi phi equal to x0. And A cos phi is equal to here, V0 plus sine omega n x0 divided by omega d. A cos phi, yeah. So A cos phi is equal to V0 plus sine omega n x0 divided by omega d. And to obtain the phi angle is equal to the arctan of A psi divided by A cosine. So you can compute the phi, and you also can compute A. A is equal to x0 divided by phi phi. This is what you can transform the analytical solution to the MATLAB code. The useful tool for you to plot the things. And I want to, teach you some basic. Maybe some of you has used MATLAB before, but I'm not sure, maybe most of you don't have much experience, but as an engineering student, I hope all of you can use MATLAB as a tool. So I define a time variable, and time will start from 0 to 6 seconds. And it will change the value every 0.01 second. So the data point will be the time will be 0, 0.01, 0.02 until 6.00. The variable time will store the value of the time. And I define the variable x to store the displacement value. But in this line, I say x equal to t so that I can build the storage of the variable with the same dimension. In this line, I just want to make x has the same dimension as t, same dimension. But the value of the x will be changed by this line of the code. I use the for loop, and for I from 1 to the length of the variable t, the x that correspond to the index I will equal to, if you remember, our xt is equal to a e power theta omega n t psi omega d t plus c. So the x is a function of the time t. And yeah, inside here, we just change the t with a small, how to say, window of time. So we change the t and we have the x that correspond to the t. And we transform this closed form solution to this code. And we know the value of phi. We know the value of omega d, the value of the damping ratio, and the natural frequency. We use the exponential function here. And until now, it seems like we have the array of the variable t or time, and we have the variable x with the same dimension as the time, and we use a function plot. It seems like you plot x and y, like here. This show the blue color. If you want to have the red color, you can do like R or red, something like that. Or if you want the red and dashed line, you can do like R and dashed line. I will show you in the program how can we plot with different type of the line. X label means this, the level of the x. Y label is this one. And the title of the plot is this one. I hope this is a very clear presentation for you, for beginner of the MATLAB to do the plot. And yeah. Okay, let's go to check the MATLAB program. I think we can see two parts of the MATLAB program. In this one is the script file. It's just like a text, how to say, we prepare the code of the program in here, but when I want to run the program, I just copy this thing and put into the main program here. Okay, when I paste the code here, as I mentioned, if we have the semicolon here, if you don't have semicolon, it will show the variable. But if we have the semicolon, if you want to know the math, you just come to the M and double click, you can see the value of the math. And the time, the metric that store the variable time, time will change from 0, 0.01, 0.02 until 6 seconds. Yeah, this is what I already described. And this is the value of the variable. The x variable has the same dimension with the time t. And when we're gonna plot, we copy the code to plot here. Picture means start the new picture, and plot x and y, and color. Grid on means you show the grid on the plot. You have x label, y label, and title. And I'm not sure you can see the plot appear on your screen. Yeah, this is the plot that appear on the screen. Okay. And if you want to learn MATLAB by yourself, it's very easy. I mean, if you don't know how to plot, you can type help and plot. When you type help and plot, they will tell you what you need to put in the plot function. You need to put x and y in the plot function. And if you put x and y and the third parameter, if the third parameter is b, is r, it will show the different color. If you put different type like here, it will plot in the different, how to say, symbol. For example, we have plot like here. And if I do like this, I add the dashed line. Let's see what we're gonna have. Yeah, now we have the blue, the dashed blue line, and no title, no X label, Y label, because we didn't put. Yes. Okay, let's continue on the PowerPoint. Okay, the following topics is the logarithmic decrement. What is the meaning of the logarithmic decrement? It means that in your system, you can measure the mass. You can measure the spring constant or obtain K from, you can obtain K from, how to say, when it drops from the equilibrium with a static displacement, you can obtain K by the static displacement, but in the real application, C is not easy to obtain. The concept of the logarithmic decrement is that we know that the damping coefficient or the damper in the system decrease or decay the magnitude of the vibration. So we can observe the magnitude of the vibration by measurement. You may put encoder to the system to measure the displacement, and the displacement decrease with the decay. So the value that you read from the displacement, you can use it to compute the value of the damping coefficient. So the equation, okay, let me write down this equation first. Okay, the logarithmic decrement is equal to log of the displacement at time t divided by another displacement when the time is t plus the period of vibration. So if you see in the picture, xt1 is here and xt2 is here. And between T1 and T2, the time difference is the period. So the magnitude of the vibration, the displacement of the vibration at the same, at the time and the time plus the period will have the ratio of the displacement. The logarithmic decrement is the log value of this ratio. So we can measure this value. So if you remember, yeah, for the underdamped free vibration case, the x equal to a e minus psi omega nt psi omega dt plus phi. So if we use this form of this solution of the underdamped vibration, the logarithmic decrement is equal to log of a e minus psi omega n t psi omega d t plus phi, and divide by a e minus psi omega n t plus the period of vibration and psi of omega d t. It should be omega dt plus omega d of the period multiplied by period and multiplied by the phi angle. Okay, what we can see here is, you know that the period of the vibration is equal to 2 pi dy by omega d. The period of the vibration here, t equal to 2 pi dy by omega d. So if the t multiplied by omega d, this term is equal to 2 pi. And the psi function of this and the psi function of this have the same value. If we check in the exponential term, this divided by this, what we have is log of the e power psi omega n t. Because t are the same, and yeah, this divided by this, you can get this one. And the log function of exponential. Finally, what we get is the logarithmic decrement is equal to psi omega n t. And if you remember that we can relate the period to the damped natural frequency, we can have psi omega n and 2 pi divided by omega d. And if you know that the omega d is equal to omega n multiplied by square root 1 subtract by psi square. Finally, what we can get here is it will equal to 2 pi psi divided by square root 1 subtract psi square. Okay. Okay. From here, what we can see from this relationship, the things that you can obtain from measurement is the logarithmic decrement, because you know how the magnitude of the vibration change when a period of time pass. You can obtain this. And this one is related to the damping ratio. But how can we obtain the damping ratio if we know the logarithmic decrement? So we need to try to change, we need to try to modify the equation to obtain the damping ratio in the terms of the logarithmic decrement. So I will begin with multiply two sides of equation by the denominator. So we're gonna have theta, the delta multiplied by square root of 1 subtract psi square equal to 2 pi psi. Does that make sense? Yeah, and you're gonna take the second power on both sides of the equation. So you're gonna have you're gonna take the second power on both sides of the equation, and you're gonna have this. And you're gonna combine these two terms together. So you're gonna have the delta square equal to the delta square plus 4 pi square of the damping ratio square. Yeah, and finally, if we want to obtain the damping ratio, it should be like this. Okay, now from the experiment, you can obtain the logarithmic decrement. And if you want to obtain the damping ratio, you can do it through this relationship. So you can get the damping ratio of the system by the experiment. And you know the relationship between the damping ratio and the value of the damping coefficient. So you can obtain C eventually. And what if we cannot measure? What if we cannot measure the displacement when just only one period passed? If we need to do it when multiple periods of time pass. We also have the relationship like here. We know that the logarithmic decrement, okay, we know the logarithmic decrement equal to log of x at any time t divided by x when the time changed by a period. It also be the same as when the time at a period t and change to the next period. It's also the same. So if you take the exponential to this equation, you're gonna have e power delta equal to the x at initial time divided by x when time passed by one period. And it also equal to when x of time passed by one period divided by when x passed by two periods. And yeah, if you multiply these two terms, what we get is E delta multiplied by E delta will equal to x at time t divided by x at time t plus period multiplied by x at time t plus period divided by x at time t plus 2 period. And yes, finally, e power 2 delta is equal to x at time t divided by x at time t plus 2 period. If we take log on both sides of the equation, what we have is log of this is equal to log of xt divided by xt plus 2 period. Okay, so finally, what we see is the logarithmic decrement is equal to 1/2 of log xt divided by xt plus 2 period. This is for 2 period. What if we consider n period of time? The value of the logarithmic decrement never change with the number of the period, because it will divide by the number of the period, and the log value will be like this. So if we consider 1 period of the value change, we use this formula. If we consider n period, we use this. And yeah, we're gonna have an example that we need to count many periods. But let's begin with this example first. We have a system. As I mentioned, we can know K and know M. We can measure K and measure M. But C is not easy to find. What if the mass equal to 2 kilograms and the spring constant is like this, 1,500 Newton per meter? And yeah, the problem gives this. And also, we said that we can measure the displacement. We can measure the displacement when x equal to t1. The displacement at time 1 equal to 9 millimeter. And when the time passed for 1 period, t2 equal to t1 plus a period, the magnitude of the vibration changed to 1 millimeter. The problem gives this information. Can we find the value of the damping coefficient? Can we find it? So we know the logarithmic decrement equal to log of x at any time divided by x at time plus period. So the value of the logarithmic decrement we know this. So the logarithmic decrement will equal to the log of 9 divided by 1. So you will compute the value of this by the calculator. And yeah, as I mentioned, if we want to go to the damping coefficient, we should go to the damping ratio first. What is the damping ratio? We have the relationship between the damping ratio and the logarithmic decrement here. So the damping ratio is equal to the delta divided by square root of delta square plus 4 pi square. Yeah, you may have question that Do you need to remember this? It's good for you to know how to derive this relationship, but in our exam, maybe if this question index is in the exam, we may not have enough time to derive. So at least I would prefer you to know how to use this relationship for multiple periods and this relationship for a single period. Maybe know how to use the formula, but I may provide you this and provide you this. So you don't need to worry, don't need to remember this, but you need to know how to use it. If this problem is gonna be in the exam problem. So yeah, from this equation, we're gonna obtain the damping ratio. And we know that the damping coefficient is equal to, how to say, no, the damping ratio is C divided by 2 square root Km. So in order to obtain C, yeah, from here you can obtain C. So yeah, you can find the value of C. Okay, next example. Next example is we have a spring mass system. We have a spring mass system. We know the mass, but we don't know the stiffness of the spring. The simplest way that we can obtain the value of the, no. Yeah, if we know the mass, we can obtain the stiffness. What if we don't know the stiffness and we don't know the mass? We don't know both parameters. Do we have any idea to modify the system and measure, and we can obtain the value of the mass and the stiffness? Yeah, I'm gonna suggest one method for the estimation of the mass and the stiffness when we don't know both parameters. We're gonna measure the the omega of the vibration. Omega is equal to 2 pi divided by the period. If you just make it vibrate and measure the time period, you can obtain the omega of this system. And then you modify a system. You modify a system by adding a weight that you know. You may add a weight of 1 kg that you know, and you make it vibrate, and you measure the period, and you obtain the omega. For example, without the added mass, the omega may be 2 radian per second. By add the mass, we add the inertia to the system, and it moves slower than the original system. The omega 2 may be equal to 1 radian per second. Just an example. Now it seems like we can compose 2 equations in order that we can solve for M and K. So we given omega 1 and omega 2. And we need to find M and K of the system. Okay, the relationship between the omega 1 and the mass is omega is equal to square root K dy by M. We have the stiffness and the mass. In case 2, omega 2 is equal to square root K dy by mass plus the mass that we know, like 1 kilogram. So yes, by these two equations, yeah, if we try to solve the equation, the omega 1 is equal to 2, omega 2 is equal to 1. Yeah, omega 1 equal to 2 radian per sec, and omega 2 equal to 1 radian per sec. Yeah, we need to find M and K. So yeah, we just take the square of this equation. We're gonna have 4 equal to K divided by M. And for this equation, we're gonna have 1 equal to K divided by M plus 1. So K equal to 4M. And here, M plus 1 equal to K. Yeah, I think from this, it's easy to obtain M and K by solving these two equations. Yeah, just do it by yourself. And we still have more 2 examples for today. This example will relate to the logarithmic decrement with multiple periods. The system give the mass value of 5 kilograms and the stiffness of 5,000 Newton per meter. And it said that the amplitude decay, to 0.25 of the initial value after 5 cycles. So the system wants us to find the value of C. The idea of this, we need to use the formula of the logarithmic decay of multiple periods. And in this case, yeah, it's 5 cycles, and it decays to 0.25. So the logarithmic decrement is equal to 1 divided by 5 of the log value of 1 divided by 0.25 Yeah, so you will compute the value so you can get the logarithmic decrement, and by the relationship of the damping ratio and the logarithmic decrement, you can obtain the damping ratio, and finally you can obtain the C. Yeah, and do we have any idea if we want to decide? This is the first part of the question. The second part is not related to the logarithmic decrement, but what if we need to find C so that the the damping, no, the damp natural frequency is equal to 9 radian per sec. Can we find C for a desired value of the damp natural frequency? The idea for a given information, we know that the omega n, or the undamped natural frequency, is equal to square root k divided by m. So we can obtain the value of the omega n. And yeah, we know that omega d equal to omega n square root 1 subtract by the damping ratio square. So if we want the omega d and we know omega n, we will know what should be the desired value of the damping ratio. And again, we need to find the C, or the damping coefficient. Yeah, this is the step for if we want to design the damper for the system. Yeah, this problem is the last example that may relate to your, how to say, your major. We have a car. We have a car suspension. We have mass. We have spring. And we have damper of a car. And yeah, given a mass of a car is about maybe 1,300 kilograms, and we know that the static displacement, the static deformation, when the car, under the effect of the weight of the car, the spring deformed by 5 centimeters. 5 centimeters. What should be the spring, constant of the spring? And what should be the damping coefficient of the damper, so that we can get the critical damp behavior? So yeah, the problem give the mass of the car, give the static displacement, and what they want us to find the spring constant and the damping coefficient for the critically damped vibration of the system. Yeah, K. We should begin with finding the stiffness. So when we draw the free body diagram of the mass, we're gonna have mass. Yeah, under the static diffraction, when the velocity is 0, we're gonna have, when it deforms with a static diffraction and doesn't move, when it doesn't move, Fd equal to Cx dot is equal to 0 when it doesn't move. So yeah, the K by the equilibrium of force in the vertical direction, we have K delta X subtract by mg equal to 0 in the static case. So K equal to mg divided by the static diffraction. So you're gonna obtain the K, or the stiffness of the spring. How about the C for critically damped? Yeah, we know that the damping ratio is C. The damping ratio is C divided by 2 square root Km. C divided by square root Km. So now we know the mass, we know the stiffness that we obtain from here. And critically damped means the damping ratio equal to 1. So now you can find C, or the damping coefficient of the car. And as I mentioned, that what's gonna happen if we have now we have a car, a cute car, and we have C and K and the mass of the car, and now the damping ratio is equal to 1. So what's gonna happen if the mass is changed from M, or mass of the car, to the mass of the car plus the mass of the human and the baggage? What's gonna happen to the damping ratio? For example, if M2, yeah, given M2 equal to maybe 200 kilogram, how this affect the damping ratio? It will increase or decrease. Yeah, please check as your maybe self-study. What's gonna happen to the damping ratio if we have the increase of the passenger mass on the car? Okay, before this, yeah, this is gonna be almost the last slide for today. Before this, we know how to derive the response of the vibration system by analytical method. And we just use MATLAB to plot the response. In this slide, we're gonna show one tool in the MATLAB. The function in the MATLAB named ODE45, which is the function developed in the MATLAB, and we don't need to do anything on it, just use it. And it can compute the same result. We can plot the same result. The result that we plot by the closed form solution, if we can find the correct solution, it will be the same as the plot that we can obtain by ODE45 function. So I'm gonna teach you how to use the ODE45 function so that when you want to practice your self-study, by change the MCK and change X0, V0. If you change this parameter, your vibration case will change to underdamped, critically damped, or overdamped. And if you change the initial condition, the vibration or the response will different. And in our class, I taught you how to obtain the response by analytical solution. And I want you to practice how to find xt for a different possible value of the parameter and initial condition, so that it comes into different type of vibration. But in order that you can check your calculation and see how it vibrates, I'm gonna teach you this tool so that you can self-check the correctness of your analytical solution at home. And this tool may be useful to validate your analytical solution in our term project in the future. So before this, we build the time function by t equal to like t0 and the change of the time and the t final. But now we can use the function t span. But the function t span will have only the t0 and t final. But the change of the time will be as minimum as possible. The computer can do the computation for you. So you guarantee that you can get the best approximation of the result. In this case, in the previous case, if you try to change this number to be like bad approximation, for example, you can have 0, 1, 6. So your time metric will have 0, 1, 2, 3 until 6. This will be the bad approximation of the time. It will not continuous. So the response will be maybe different or maybe the same. You may try to check. But if you use time span, yeah, the difference between time will be the minimum possible, maybe 0.0001 or less than that. Yeah. And to use the function ODE45, this will be the value that the function gives you back. The function will give you the variable y and give you the time back. And the input to the function, is the variable time span and initial condition. Initial condition here consists of the velocity at time 0 and the position at time 0 by the order v and x. In the next slide, I will explain why v come before x0. And as I mentioned, the output of the function will be the time, and the output function, the variable y will store two things. The variable y will store x dot and x. This means you consider the second component of the y. If you pick this, you're gonna see x. If you use y colon and 1, what you gonna take from the variable y is x dot or velocity. But if you select the second column in the second row in the y variable, you're gonna have the displacement, not the velocity. In the next slide, we'll show why the y variable can store this parameter for the function ODE 45. This is on the main program, but you need to generate the function program here. In the function program, we have the function name and the variable that will be returned. The variable that we gonna use and the variable that we gonna return. YP, or the variable that we gonna return, is this one. YP is this one. So you can see that YP is the same thing like here. The first one, the first component of the YP is the thing before the semicolon is related to the x dot. And the second component is related to x. In the next slide, I will tell you why this one is related to this. But instead of solving the equation by hand, by analytical way, and do the plot on MATLAB, you can just use this line of the code, and you can obtain the xt through this. And you do the plot. You do the plot here. In your plot, you just plot time t, and the second component of the YP, which is the position here. And you can plot the red line in here. And the second part here is the one that you do by the closed form solution, and it plot in the blue line. You can see they completely fit between the ODE 45 and the closed form if you derive the correct closed form solution for xt. And the command legend will create this legend box for you. The first plot and the second plot by the order, the name by the order. Okay, in here, how can we describe the YP of the ODE 45? Yeah, this slide may take more 5 minutes, and today we will delay for 5 minutes, okay? The second order equation, mx dot dot plus cx dot plus kx equal to ft. We're gonna select a state variable y1 equal to x dot and y2 equal to x as a state variable. From this equation, we can write down this equation as okay, x dot dot is equal to minus c per m x dot minus k per m x plus 1 per m ft. This is the relationship between the x dot dot. You may not need to, how to say, fully understand this derivation at this time, but maybe in the next 4 or 5 weeks, yeah, we will study this thing again. But this is the, how to say, how the ODE 45 function works. And yeah, this is the relationship, first relationship that we can transform for here. And another one is x dot is equal to the x dot. Y1 is equal to x dot and y2 is equal to x. This one is y2 dot. What if I want to write this in a metric form? If I want to write this in a metric form in the terms of y, I'm gonna have y1 and y2 dot equal to y1 and y2 dot equal to minus c per m minus k per m of y1 and y2 plus something here multiplied by ft for the input force. Okay, it should be 1 per m. Okay, the first equation here is correspond to this one. Y1 dot is x dot dot and minus c per m multiplied by y1. Y1 here is x dot minus k per m multiplied by y2. Y2 here is x plus 1 per m multiplied by ft is this one. And the second equation, y2 dot is equal to y1 because y1 is equal to x dot. Y2 dot is equal to y1. So y2 dot is equal to y1. So Yeah. If we write this into this form, how to say, you can see the minus c per m multiplied by y1 and minus k per m multiplied by y2 will be the first how to say, first variable that's stored in the yp, and the second one that's stored in the yp is just only 1 multiplied by y1. Yeah, so yeah, it's still complicated for you, but in order to use this function, if you want to use this function, please pay a little more attention to this. It's important how to use the function because we have a function here, not in the main program. So let me show you one thing. On my screen. Okay, wait a second. Okay, in MATLAB, I built one function file. The function file is on my desktop, and the name of the function file has the same name with the function. And the variable that is the input of the function is time, and the variable y, and the output of the function is yp. That is a metric that stores two values. The first value is the ratio multiplied by the first state variable, and the k divided by m multiplied by the second state variable. The first state variable is the velocity. The second state variable is the displacement. And yeah, the second variable in yp is the displacement. No, is the speed, is the velocity. Is related to the metric that we derive, but you just build this function file in your, how to say, in the folder that you're gonna run the MATLAB code. And in this function file just has the mass, the spring, and the damping coefficient, and this function to return the value of the variable. This is the function file that I put on the desktop. And in order to call this function file, you need to go into the main of the MATLAB. Let me see, we have the MATLAB here. Wow. Okay. The code that I put on the PowerPoint, if we copy the code on the PowerPoint and place on the main, what we're gonna have is here. Okay, before do this, I will delete everything here. Okay, and no more variable store here. We place here. The function that we're gonna put is the time span from 0 to 6 seconds. And the initial condition, velocity is 0. Initial displacement, x0 is 0.1 meter. And we use the ODE 45 function. The name of the function is the unforced one that we put on the desktop. I put unforced one function file on the desktop. And yeah, the input to the function is the time and the initial condition. And the function will return time and y. But in this y, we have the column 1 and column 2. The column 1 is velocity. Column 2 is the displacement. So we're gonna plot only the time and the displacement. So we will use this plot function. So if I enter, we will see this plot. And on this plot is the red plot. And the plot is the result of ODE 45. And if I put another plot by our cross-form solution, it will be this one. By our cross-form solution, we have the t, or the time function, and the displacement that relate to the cross-form solution. And we're gonna plot, if you see here, there is a message, hold on. Hold on means after we plot the red plot by the ODE 45, the plot of MATLAB still on. And if we put a new function of plot, it will plot on the same plot as the previous plot. But if you want to begin a new plot, you need to put a fixture before plot. It will plot a separate plot. So after this, we still hold on the fixture of the previous plot. And now we're gonna plot the new plot with the color of blue. Grid on is mean it's gonna show the grid. And the legend, we'll put the legend to the previous plot of ODE 45 and the legend for the new plot, which come from the cross-form solution. And then I press the enter. And they say undefined function or variable a. The a is come from our previous, the cross-form solution. I need to put from the beginning, sorry. Okay, we need to put this computation, original computation, that we compute A, which is the amplitude that relate to the value that we get. Okay, I will try to plot the analytical solution again. Okay. Okay, now no more error message. And if we go back to see the picture of the plot, wait a second. Okay, so in the picture of the plot, now we can see that we have the ODE 45 that we plot it first, and the cross-form solution that we plot it later. So the last one will on the top of the first one. So we cannot see the red because it's beneath the blue one. Yeah, I hope you will review the MATLAB program. And if you have any question, we can have extra discussion. At least if you try to follow my code and know how to put the function file in the same folder of the MATLAB directory, I mean, you can change the MATLAB directory here. And wait, yeah, you can change the MATLAB directory here by these things, and you should select the folder that you put the function file. For example, my directory is on the desktop, and I put the function name unforced1 on the desktop. And if you call for the function, it can find the file, the function file. Yeah, you can make a plot, I think. Okay. Yeah, more than enough for today. We have a long day, and sorry that I late for 15 minutes. Yeah, if you have any question, please ask question. And if some guy don't have any question, yeah, the class is terminated for today. And see you next week. Thank you. Bye-bye.